So it's a pleasure to introduce the final speaker of this geometry section of the 2014 ICM, Peter Topping, a former collaborator from Warwick. He received his PhD in 1997 from Warwick under the direction of Miriam McAuliffe. He changed jobs every year for the next 4 years after that. Went through a succession of postdoctoral positions at the ETH in Zurich, the IHES in Paris, MSRI in Berkeley, and Cornell, before returning to Warwick, where he's now a professor. He received the Whitehead Prize in the London Mathematical Society in 2005, the Leverton Prize in 2006, and his research has been generously spread by the Leverton Trust since that time. He's going to tell us about Ricci flows with unbounded curvature.
Okay, thank you. Thanks, Robert. So I'd like to talk about geometric flows. So this is a subject which is 50 years old this year. It started with the pioneering work of Eels and Sampson from 1964. And more specifically, I'm going to be talking about the Ricci flow. So this is a slightly younger geometric flow, but one that many of you will know, especially if you've been into the last couple of ICMs. It's been discussed extensively, and even this one, you will have heard about it. So let me start by giving a definition of Ricci flow. I won't assume you know anything about this. So let me not assume that you even know anything about Ricci curvature. So the Ricci flow is a time-dependent family of Riemannian metrics on a manifold, say vaguely n, of dimension n. And it satisfies the partial differential equation given there. So dg by dt is minus 2 times the Ricci tensor. So the Ricci tensor you can think of in several useful ways. So maybe you should think of the right-hand side, so minus the Ricci tensor, as a sort of Laplacian of the metric. So that's kind of convenient for intuition. So this is, you should think of as a heat equation. So if you have a manifold with some sort of corners or some pointy parts, then this flow heuristically, intuitively, will try to smooth those out. So maybe some intuition from 2 dimensions. I'll talk about this a little bit more. So having in 2 dimensions, the Ricci curvature is a little bit like the Gauss curvature. So if you have any intuition about surfaces, then maybe the Gauss curvature can be a useful way of viewing this Ricci tensor. So I'm going to put up a few applications that the Ricci flow has had, and I've mixed them up with a few potential applications, and some of these sections are both applications and potential applications. So the first one is surely the most famous. So Karaman's proof of the Poincare conjecture and the geometrization conjecture we've heard about a few times already. And following Hamilton's program that he developed very successfully for many years. Uniformization results, well actually I'll be coming back to that in a second, so let me not say too much about that. Some potential applications in that direction would be in the setting of Kähler manifolds. So, for instance, Yau's conjecture that you have an open Kähler manifold with positive bisectional curvature, then it should be biholomorphic to CM. So that's a potential application of Ricci flow, of which there's been much partial progress on electron survey. Section 3 here, understanding the topology of manifolds with certain curvature restrictions. So this is a big deal. It's been a very successful topic. I'll give one example in a second, in fact the original example. And there are many others. Again, I won't try to survey everything. Spectral theory is a little bit less well known perhaps, and that covers several things. But for instance, the determinant of the Laplacian, if you know what that is monotonic under Ricci flow in simple situations, possibly in all situations. And so you can use that to prove various results. Current, moving a couple down, a current area of activity is in smoothing of rough spaces. So for instance, you have certain metric spaces with some extra structure, then the Ricci flow can often smooth them out to make them Riemannian manifolds, and there are many applications I won't try and survey. Okay, so let's think briefly about Hamilton's original application, or applications. So in the paper where he introduced Ricci flow in 1982, he showed that the Ricci flow deforms any simply connected closed three-manifold with positive Ricci curvature to the round sphere S3, so if you normalize the flow at least. So it converges to a round sphere as time goes to infinity, and all the way along the flow, the Ricci curvature is positive. So when I say normalized Ricci flow, what I really mean is you do the Ricci flow, but as the volume changes, then you keep homothetically dilating or shrinking so that the volume is fixed. So a round sphere, for instance, under the Ricci flow would shrink down and in a finite time end up at nothing. If you normalize the flow, it would just stay fixed. Okay, so a consequence then, which is very out of date now, but it's kind of appropriate for this talk, is that if you have a three-manifold, a closed three-manifold with this curvature condition, then it's diffeomorphic to S3. So we know much more than that now, of course, because of the work of Curvature. Also, if you have just a general closed three-manifold with positive Ricci, that must be a spherical space form. So this is all very well known. What's maybe less known to non-experts is the slightly later application of Ricci flow by Hamilton to the more general situation where the Ricci curvature is non-negative. So again, if you don't have any intuition for Ricci curvature, that's only going to cause minor problems for a couple of slides. Think of surfaces. So positive Ricci curvature for a three-manifold, think of it a little bit like a positive Gauss curvature surface. So Hamilton showed that you can use Ricci flow in quite a different way to do this generalization to non-negative Ricci flow. So he showed that if you take a closed manifold with non-negative Ricci flow and you flow it just instantaneously now, we're not interested in the long-time asymptotics, just instantaneously, then there's a certain strong maximum principle. So think of the strong maximum principle for scalar functions. If you have a heat equation, say, and you have a function which is non-negative, then either it becomes strictly positive straight away, or it's identically zero. So there's an analog here. So if you have a Ricci non-negative manifold, then the Ricci flow is a little bit like a parabolic equation for the Ricci tensor, as it turns out. So either you're strictly Ricci positive, or, well, not quite your Ricci flat, but the manifold splits locally as a product. So you might have like S2 cross S1 would be an example to keep in mind. So that allows you to classify this slightly more general class of manifolds. Okay, so these, what I'm talking about here, closed three manifolds, so in particular compact, no boundary. Okay, so a few years later, then she, a student of Yao, I think, showed that if you were to flow an open three-manifold, so complete non-compact now, with non-negative Ricci curvature, if you could just flow instantaneously, then you could do the same strategy as before. So either you're Ricci positive, in which case you would know from minimal surface theory, work of Shane Yao, what your manifold was. Or you would get some splitting, so you could again classify. So the reason I'm telling you this is so basically, because you can't do this. So this is a problem even to this day. We don't know how to flow a general open three-manifold with non-negative Ricci curvature, even for a short time. So certainly we think that you can do that, but we don't even know how to do it for a short time, which is all you need for this application. So in some sense, this is not a disaster because you can solve the application in this particular case with minimal surface theory. Eventually, this was shown by Yu, 2013, I think. Nevertheless, there's a simple, compelling argument at the top here that she was trying to carry out, and it's hampered by the fact that you just can't deal with Ricci flows of unbounded curvature. So that's really what I want to talk about. So, so that's going to be the topic of the talk. So the problem here really is that the manifold might have unbounded curvature. So there was a result that Xi proved in his work. So that's an extension of Hamilton's original work on closed manifolds. So I've combined it into one result. And they show that you can actually flow your manifold if it has bounded curvature. So if you start off with bounded curvature, then there exists a Ricci flow with that initial G0 for a short time. In fact, you know a bit about what this time is. So either you can flow for all time, or if the time is finite, then the curvature blows up. So you start off with bounded curvature, you would flow with bounded curvature, the curvature would go up, it would go off to infinity maybe, and then you'd stop. So for instance, you could imagine a shrinking sphere. As it shrinks to nothing, then the curvature blows up until it disappears when the curvature goes to infinity. Okay, so so the time capital T has traditionally been called the maximal existence time, the Ricci flow. Although actually, from what I'm about to explain to you, that terminology no longer makes sense. So you'll see why in a second. Okay, so the flow I've mentioned here in the top few lines has bounded curvature, as I said, until you get to maybe capital T, it's finite. And that bounded curvature is enough to show that your metric remains complete. Okay? So, complete you could characterize as meaning that if you have a proper curve, so a curve heading out to infinity, then it should be infinitely long, always. So, you start off like that, so any curve heading up to infinity is infinitely long. And the bounded curvature is, using a one-line calculation, is enough to show that the distances, lengths of curves, can only increase or decrease at most exponentially. So certainly, this infinitely long curve heading out to infinity cannot suddenly become finite. Okay, so incidentally, I should mention that Xi could, because he could flow these manifolds, he could at least classify the bounded curvature manifolds from the last slide. Okay, but a little window into why unbounded curvature is so difficult is that completeness can suddenly fail if you have unbounded curvature. So here's a theorem. So there exist Ricci flows starting with completely nice, smooth, complete Riemannian manifolds of bounded curvature that are incomplete as you start flowing. Or, if you like, you can have them complete for a while and then suddenly become incomplete at the time you're choosing. So let me give you a sketch of one of the examples here. So, if you take a torus with any conformal structure and remove any point, then there exists a unique, complete hyperbolic metric with that conformal structure. And incidentally, you could plug that hyperbolic metric into the top theorem and you would have a Ricci flow. It would just be the Ricci flow which took this hyperbolic metric and just expanded it homothetically. It's sort of the opposite of a shrinking sphere. So the example here says that there's something else you can do. So the way I phrased it here, I said there exists a Ricci flow on the whole torus now, so that as you go back in time, you converge to this age, at least away from the punctual. So this is maybe a little bit hard to see what's going on, although I can explain best with a picture. So here's the picture. So the top two lines are copied from the last slide. So on the left of these, the leftmost of these three pictures is supposed to represent this hyperbolic metric on the once punctual torus. Okay, so maybe you have a hyperbolic cusp where the puncture is. So as I say, you could flow that and it would just expand homothetically with Xi's flow. And the example here, the theorem here, says that in fact what you can do is you can add in a point at infinity. So if it may be easier to imagine this going really a long, long way out on the cusp, and then just capping it off, and then flowing that. So really infinitely far along the cusp, and then capping that off. So the theorem asserts the existence of a Ricci flow, which looks a little bit like the next two pictures. So the cusp comes flying in from infinity, and gradually the diameter shrinks in a way that you can actually explain very precisely, and eventually the metric will just become flat, in fact, in this case. So in particular, this gives an example of incompleteness for the following reason. I mean, you can take, instead of viewing the Ricci flow on the whole torus, just now remove the point P. So then you get a completely nice, smooth Ricci flow on the punctured torus. And it starts off like on the left, and then as soon as you get going, it's now incomplete. Because you could take a curve going off to this puncture P. So that would be a proper curve heading off to infinity. But it would have, of course, finite length, so it's no longer complete. So the point P is being pulled in from infinity, if you like. That's one way of seeing it. So you can think of this as a, just to get a little bit philosophical for a minute. So you can think of it as the, using this sort of intuition, that unbounded curvature allows Ricci flow to feel infinity. So it's often useful for intuition to think of Ricci flow as some sort of analog computer. You know, you feed in a starting metric and it processes it for you. So in this unbounded curvature, contrary to all the traditional theory, Ricci flow can pass information back and forth to infinity. So actually, this whole topic of how Ricci flow keeps information local, or maybe doesn't, is actually a really interesting topic. It's kind of a key part of theory, which often gets hidden in talks. You don't necessarily need to discuss that to mention applications. Okay. So I want to discuss one particular situation where we can actually see what's going on really explicitly, and the theory is actually pretty clean, though it somehow a little bit weird as it turns out. So that's a situation where the underlying manifold is two-dimensional. So we have a surface. So if you've been uncomfortable, if you're not a differential geometer and you've been uncomfortable with the Ricci tensor, then you can actually really just think in terms of Gauss curvature now. So the Ricci tensor in 2 dimensions is just the Gauss curvature times the metric. Okay? So the equation simplifies, like I've written here. So it now is an equation of the form dg by dt is some function times g. That function happens to be minus the Gauss curvature. And one nice feature of that, which isn't present for our higher dimensions, is that the flow makes a conformal deformation of metric. Okay? So in particular, isothermal coordinates at time 0 remain isothermal coordinates at later times. So what isothermal coordinates? So of course, these classical things are coordinates x and y, so that you can write your metric as some function times the Euclidean metric. So some function times dx squared plus dy squared. So there's no dx tensor dy term. So this is something that you can do in 2 dimensions, not necessarily in higher dimensions. So u is just a function on that. So if you do that, then you can plug this form of g into the equation here and just derive what is the equation satisfied by u. So it turns out that it satisfies this equation here, the so-called logarithmic fast diffusion equation. So this is actually a very well studied equation. There's a huge literature on this. Normally it's considered on almost always is considered for functions capital U on the whole of R2. So just to explain what's going on here, because we're working on manifolds, this Laplacian really is just a sort of standard Laplacian in local coordinates. So for some purposes, a nicer way of writing the equation is to write u as e to the 2 little u. And then the equation for little u is written on the bottom. I hope you can see it at the back. So du by dt is e to the minus 2u Laplacian u. So it's a heat equation, so you can really see what's going on now. U is just a scalar function. but you've got this factor e to the minus 2u, which is sort of speeding up diffusion or slowing it down, depending on whether u is large or very positive or very negative. Although that notion of whether u is large or not really depends on the coordinates. So different people with different coordinates would come to a different conclusion about whether you're in such a region. And let me just point out that the right-hand side of the equation is simply a way of writing minus against curvature. Okay. So let me give you a theorem about Ricci flow on surfaces, on closed surfaces, in fact. So this is a theorem of Hamilton, and it's a combination of theorems of Hamilton and Chow. Actually, Chow's work is not quite in the 1980s, or I think it was published in 1991. So what they say is that if you take a Riemannian metric on a closed surface, so compact, no boundary, then there exists a nice Ricci flow and it does something nice for you. So there exists a unique smooth Ricci flow, G of t, starting at the metric that it should start at. And it exists for a time interval that you can actually write down explicitly. So let's say if you were in the oriental case, then you'd be in the top line here if you had a sphere. If your underlying surface was a sphere, in which case this would be 1 over 8 pi times the volume. And in every other case, the flow would exist for all time. So not only do you have the existence of this flow, but you also know what it does. So it finds a metric of constant curvature. So it's the best you can hope for, in a sense. So the way I've written it here, which is a little bit weird, let me actually explain it in words before, in a slightly different way, before trying to pass that bottom statement. So if you were to do the normalized Ricci flow, so you kept on homothetically adjusting so that the area stayed fixed, then you would converge to a metric of constant curvature as time goes to infinity. So without that renormalization, then in this top case, I think this is like the sphere case, then you have to adjust for the fact that the sphere is shrinking. Maybe it's not a round sphere in general, but you have to rescale the metric. So you do that in this way. So 1 over the time left to the singularity is the scaling factor for G, and then it will just converge nicely as CK, everything you would go for, to a round metric on a sphere. Similarly, if you're in the sort of torus case, if you like, then now you don't even need any normalization. It just converges to a flat metric. And in the hyperbolic case, actually this will crop up. This will be relevant later, so particularly important. If you're now scaled down the metric, then you'll converge to a hyperbolic metric. Okay? So everything you'd hope for somehow is true. Actually, this theorem is perhaps a little bit misleading. It reminds you maybe of how a heat equation would make a function into a constant function, as if there's nothing exotic going on here. But actually, it is a little bit weird how the flow does this. So for instance, let's just look at the sphere case. So let's say your starting metric was a sphere which was really 2 spheres connected by a thin neck. Okay, so just imagine 2, no blackboard unfortunately, but just imagine two big spheres and you just connect them by a thin neck. So maybe the intuition would be that the sphere should shrink and the neck should just expand, and eventually it would become a positive Gauss curvature and then just shrink down to nothing. But actually it's not quite how it works. I mean, spheres would just fly out to make the surface have enormous diameter. Then the diameter would stabilize, the spheres would shrink, and then suddenly you'd have a very long thin cylinder which would come flying back in again. So there is some sort of geometric complexity going on here which has never really been studied, I would say. Perhaps should be. Anyway, one consequence of this sort of tautology is that the Ricci flow is geometrizing the closed surfaces. So you can, for what it's worth, prove the uniformization theorem this way. It would at least close surfaces. Okay, so, I mean, given that it's only for closed surfaces, what about for non-compact surfaces? Okay, so then things get a lot more tricky in a way that we really haven't envisaged. So let me try and motivate that statement. Okay, so let's just for this slide, let's just consider for the moment only complete surfaces. Okay, so if we imagine we have a non-compact surface, and we have a Riemannian metric of bounded curvature, then we can flow it using this Hamilton sheaf flow that we had from before. So that we can at least flow for a certain time. So you can ask the question, well, maybe the theorem from before is just a really special case of some much more general statement. When you flow with sheaf flow, will it geometrize the surface? Which by simply, all I mean by that is, will it find a metric? Will it flow nicely and find a metric of constant curvature? So the answer actually is no. And for a very weird reason that we really wouldn't have expected a few years ago. So you can, it'll be a consequence of what I'm going to explain in a minute. It would be the following theorem. So to deform some bounded curvature surfaces, so some really nice, smooth, bounded curvature, complete surfaces, to deform them into constant curvature surfaces, so to do this geometrization I was mentioning, just in exactly the same way as works in the Hamilton-Chow theorem I just explained, then the Ricci flow must pass through surfaces of unbounded curvature. So this is a little bit weird because why should that be? I mean, if you take a nice bounded curvature surface, then you could deform it somehow without going through unbounded curvature to your nice limit metric, maybe your hyperbolic metric or your flat metric or whatever. But the Ricci flow simply can never do that. So, in particular, sheaf flow will never uniformize one of these surfaces, because sheaf flow will flow at least as long as you have bounded curvature. At some point, you have unbounded curvature, maybe, and then you stop. So none of these surfaces that I'm talking about in this theorem could possibly be uniformized by this Hamilton sheaf flow. So the actual content of this theorem here is a little bit unclear because, you know, it's reasonable to ask, well, what sort of existence or uniqueness do we have here? You know, why can we even, you know, what's the significance? So let me look a little bit ahead to explain what we proved a few years ago, as I'll describe in a second. So also with Gregor Eason here, we proved that you have existence of solutions to Ricci flow. You have existence of Ricci flows starting with these bounded curvature surfaces. So uniqueness is very unclear, at least at that point. And we also proved that you have convergence to constant curvature metrics. So there's something very weird going on here, right? So what we didn't realize at the time was that, basically a consequence of this theorem, that even though you're starting at a nice bounded curvature, complete, smooth, everything nice metric, and you're converging in the nicest possible uniform CK way to, in fact, a hyperbolic metric, somewhere in the middle you must have unbounded curvature, and there's no way of getting around that, whatever sort of non-uniqueness you may have had. So then the reason for that is somewhat, I mean, it will pop out directly from the theory, but there may be some other reason that we don't understand. There may be some sort of theoretical reason. I mean, in geometric flows you often have situations where, in theory, you could have your geometric flow converging directly from some arbitrary object to your nice or limiting object without any singularities, but the flow necessarily has to develop a singularity. And you can often find theoretical reasons why that is the case. So somehow the full picture here is still a little bit unclear. So as I've just said, we have an alternative existence theory that can actually do this, that I'll describe now. So not only will this existence theory start off with a metric like this, a bounded curvature complete metric, it would even be happy starting off with an unbounded curvature metric, and even with an incomplete metric. So there's a full existence theory, which I hope to convince you is the right way of seeing this. But this is very unfamiliar territory, you know, starting off with unbounded curvature, starting off with incomplete metrics is even weirder. So let me try and explain how that can generate very weird behavior, although somehow unbounded curvature and incompleteness are very sort of closely linked in this game. So there's a simple example that I've understood for some time now. The simplest example, which is to consider starting a Ricci flow, starting at a flat disk. So a flat disk obviously is an incomplete metric. You can get off to infinity in your disk by traveling a distance less than 1. It doesn't have to be infinite. So how would you possibly do a Ricci flow starting this? Well, of course, there is the stupid Ricci flow, perhaps. From some points of view, the natural Ricci flow, you just stay as a disk. So that would be a Ricci flow. But let's look at this a little bit more closely. So let's go back to a couple of slides to where I wrote G of t was capital U times the Euclidean metric. So I said at that point that the equation that U satisfied was this equation here. So it's a nice parabolic equation. It's a bit like a heat equation, but you put the central factor. So what is the PDE problem that this Ricci flow would actually satisfy? Well, of course this, with the auxiliary condition, you start off with a flat disk. So in other words, you start off with this e to the 2u is just 1. So u is just 0. So in the preceding paper I managed to not write this down correctly. Okay, so the point to notice from looking at this is that we need a boundary condition for this to be a sensible equation. So basic parabolic theory. So for instance, just consider the heat, if we just had the heat equation, so without this e to the minus 2u. Basic parabolic theory says that you can solve a parabolic equation with initial data. So here we have initial data, as long as you give boundary data. So it would be a nice well-posed problem just to consider u's, which were continuous up to the boundary of the disk, and then add an extra condition, which is basically to specify what u is on the boundary. So if you were to do that, you have existence of solutions and uniqueness. Okay? So one could do that, but it wouldn't necessarily be the most geometric thing to do. As maybe I can try and convince you. So in an alternative, I gave almost 10 years ago now, which was, instead of a boundary condition, you should ask that the flow is instantaneously complete. So all I mean by that is that for all positive times, the flow, the metric g of t is complete. So it needn't be complete at time 0, but we want it to immediately become complete. So what does that actually look like? So think of this as some sort of growth condition for you, but of a very unconventional form from a PDE perspective. So it's saying that if you take any curve going out to infinity, so think of a curve heading from somewhere in the disk out to the boundary, if you like, though I really think of my disk as not having a boundary, it's an open disk, then the conformal factor has to grow, so u has to grow sufficiently fast so that the length of this curve is infinite. So the length, of course, is just the integral of e to the u. So u has to grow somehow as you head out to the boundary, but not necessarily in a uniform way. It's just that if you took any curve, then it would have to pass through regions where u were large. So what I realized some time ago is that for some surfaces, I didn't know which surfaces, and I didn't know quite what happened, but for some surfaces, so including the disk case at least, then you can do this. You can find solutions, and they have this instantaneous completeness. So if you've never seen this before, then a picture is in order. So what does the conformal factor look like for a small time? So I'm trying to draw a picture here. So in the picture, you have the disk here, and I'm trying to draw a graph of u. So it starts off just 0. But a little bit later on, u will be almost 0 on the interior here, but it will blow up as you go out to the boundary. Okay? So, and it blows up in such a way so that if you integrate e to the u, then you get infinity as you go out. So you think of this as taking the disk where the boundary is a finite distance away, and it immediately pushes the boundary out to infinity. It's sort of a little bit opposite of the example we had towards the beginning of the talk, where the cusp was being pulled in from infinity. So you can say what's happening to you here. It's not blowing up in an arbitrary way. In fact, you can give a geometric explanation. So this is a little bit like the conform factor of a Poincare metric, so the hyperbolic metric on the whole disk, at least if you were to scale it so that the curvature were -1 on 2t, then in some boundary layer here of the disk, it would behave in that way. Okay. So a weird feature that I realized back then about this example is that there is actually only one way that the flow can do this in this example. So it feels like you're feeding in heat, if you like. You're feeding in metric at the boundary, and there should be lots of ways that you can do that in general, or in this case, for instance. But that actually turns out not to be the case. So the intuition is that if you try to feed in less to the boundary, less u, if you like, then you won't actually achieve completeness. Okay? If you were to try and feed more in, then, well, in the equation, which I've written at the top here, this e to the -2u would dampen the diffusion into the interior, so the heat would never get there. So once you put in a certain amount, it's slowing the diffusion down so that you get uniqueness. Okay? So this actually turns out, we realized, now working with Gregor Giesman, initially, a few years ago, we proved a well-posted theorem that can actually not just deal with the flat disk, but can deal with really any metric, any smooth initial metric. So it doesn't have to be complete, and it doesn't have to have unbounded curvature. And moreover, you can say, it's not just a short-time existence result, you can say exactly for how long the flow must exist. So, how long should it exist? So if you give me the metric G0 on the surface, then I'm going to define for you the existence time, capital T, in the following way. So it's a little bit like in the Hamilton-Chow result. In fact, we're incorporating that result into here, and a bunch of results of the logarithmic constitution equation, I should mention, which I won't try and survey. There's more in the proceedings paper. So the existence time here is, as I say, a little. That's exactly actually how I wrote it in the Hamilton-Chow theorem. So now, instead of just having S2 or RP2, which was what you get in the Hamilton-Chow theorem, you could have this top case also covers the non-compact situation where the underlying manifold is the whole plane. So in that case, of course, because you're in a non-compact situation, volume could be infinite, but that's fine. That's even better, in fact. You just have infinity on the top there in that situation. Anyway, in every other case, which in some sense, if you're a hyperbolic geometer maybe, in most senses, then the existence time is infinite. Okay? So once you've got that existence time, then the statement of the theorem says there exists a Ricci flow starting with your G0, given G0, completely arbitrary, could be as badly behaved as you like, and it's instantaneously complete. So not only do you have those two properties, but after a long time of struggling with this, last year I managed to prove that would then imply uniqueness, which starts having all these weird properties about the way Ricci flow geometrizes surfaces. Okay, some more properties about this flow. Has a nice curvature lower bound, and has a maximally stretched property. And I think maybe I'll skip the description of that. You can look in the proceedings paper if you want that. I won't need it right now. And if t is not infinity, then really the flow just disappears. So the volume converges to 0. So you couldn't ever hope to continue any further. Okay, so capital T, I think you can reasonably call capital T the maximal existence time. Okay. Right, so let's talk about some more properties of the solution. So, what might have been the case, so let me just rewind very briefly. So what might have been the case is that if you plug in a weird metric here, maybe with unbounded curvature or incomplete, well, it certainly immediately makes it complete. And maybe, in fact this is what we thought when we originally proved the result, maybe it would make the metric immediately a bounded curvature. And certainly we do have a lower curvature bound here. In which case we'd sort of be in this classical situation straight away, be in that she situation. So what we realized somewhat later, 2011, is that actually that's not the case in general. So, and can't be the case, so because of this uniqueness result. So on any non-compact surface, a Riemann surface, so you specify the conformal structure, there exists a conformal Ricci flow with unbounded curvature for all time. Okay? So the Ricci flow there necessarily is the Ricci flow that I mentioned in the theorem before, because you have a uniqueness statement. Okay? So let's look at a simpler situation. So in this situation, we have unbounded curvature initially, and it just stays unbounded. So that's slightly odd behavior, which we're going to use on the next and final slide. Let's look at an even simpler, apparently even simpler situation. So this is the situation where she's flow would work. So complete bounded curvature, initial metric. So you could now flow that in two different ways. You could flow it with she, Hamilton she, or you could flow it with the theorem from the last slide. So the uniqueness theorem, which I didn't specify very carefully on the last slide, the uniqueness theorem would say that they necessarily have to be the same flow. But more precisely, they have to be the same flow while they both exist. Now the point is, our flow must exist at least as long, because the only way you can stop it is by making the volume go to zero. But in fact, so the theorem from last year is that you can find Ricci flows from this existence theorem. So you start off very nice, bounded curvature. I'm plotting here the supreme of the curvature. But then the curvature blows up. So at that point, the curvature is blown up. So this is a point where she's flow ends. So that used to be called the maximal existence time. So that doesn't make any sense anymore, because our flow carries on. So the flows we construct have unbounded curvature for a while, and then, well, or forever perhaps, or, as I've drawn here, at some point they start having bounded curvature again. So it's kind of weird behavior perhaps. But you'll see that it has some sort of bearing on this uniformization question, for instance. Okay, so final slide. Let's go back to this question of geometrization. So I just simply mean the study of, well in this context I mean the study of how the Ricci flow does or doesn't find a constant curvature metric. So I remind you that on closed surfaces, everything is very nice. Hamilton Chow says that the Ricci flow geometrizes the metric, makes it constant in the nicest possible way, in a CK conversion theorem. So what about in the non-compact case? Well, actually, this is still, in full generality, still an open problem. But at least now we have a flow that we can ask this question. We have a flow which will exist for the right amount of time, in some sense, that it might do the job. So, moreover, in some sense, most cases, the flow will do the job. So here's a theorem from 2011. Actually, we managed to prove the theorem without really understanding what was the full sort of implications of the theorem. So it says that if you start off with an initial metric which could possibly find a hyperbolic metric, so one that's conformal to a hyperbolic metric. Okay, so it's always, the metric is always either conformal basically to the sphere, or the universal cover of C, or or this case. So where you're conformal to a hyperbolic metric. So the theorem says, well, the existence theorem from before says the Ricci flow exists for all time. But this theorem says that it will find this hyperbolic metric. So it converges to the hyperbolic metric. Okay? So what we didn't realize, that I mentioned much earlier in the talk, is that there are some weird situations where you start off with completely nice, complete bounded curvature metrics, and they're going to converge completely nicely to a hyperbolic metric, and CK uniformly, everything you could possibly hope for. And yet, somewhere in the middle, there has to be surfaces of unbounded curvature. That's a sort of theoretical fact. So that's a much more recent realization that there's all this sort of extra behavior. So finally, let me just reconcile this theorem with the other result from the last slide. So what was the first result from the last slide? That said that on any Riemann surface that's not compact, there exists an initial metric, the unbounded curvature. So when you flow it, you keep on having unbounded curvature. So how can that possibly be reconciled with this theorem here? Because I could take one such metric that's conformal to a hyperbolic metric. I mean, just take one on the open disk, for instance. That's certainly conformal to a hyperbolic metric. So one theorem says that the curvature remains unbounded for all time, but this theorem says the curvature converges to -1, even after rescaling. So in fact it converges to 0. So how can it be unbounded and also converge to 0? Well, of course, the key for that theorem is that that convergence would then only be smooth and local. So somehow the Ricci flow organized itself so that on any compact region, the curvature becomes under control and you get geometrization. And then the regions which the regions which have unbounded curvature, which necessarily must exist, they all get shot out to infinity. So they get sort of squeezed out to infinity. So somehow the Ricci flow can organize itself in that way. And the theorems are then compatible with each other. So I'll stop there. Thank you.
Further questions or comments? Okay, so sorry, where?
I have a question about the flow of the disk. You said instantly the flow of the disk, and we have at the boundary we have infinite curvature. I think then there is the solution of the disk flow is not continuous. What do you mean by instantly?
Right, so the question was, let's go back to the case where the disk is flowing, and whoops, and the concern was that the metric is not continuous. So, and maybe I've stated that the flow is completely smooth. So the point is that the flow is completely smooth on this. All the singularity is happening at the boundary. So it's like happening in infinity. So if you stand anywhere on this disk, even if you're very close to the boundary, if you just stand there, initially you're at 0. You take a little disk, open disk around yourself here in the disk, then you start off at 0, and the U here restricted to that disk is completely C-infinity smooth. The point is that the sort of singular behavior is coming flying in from infinity. It's a little bit like in the collapsing cusp situation, where everything is totally smooth. The singular behavior is at spatial infinity at one instant in time. So it's not really clear what's happening here. A little bit later in time, the U would look like this. So maybe it's more easy to visualize if you go backwards in time. So it's like this at some time, and then a little bit earlier, it's more down, and you're basically sort of shrink-wrapping the graph onto the disk connected to this path slider. Okay?
For Chad?
So I was wanting to ask, is there some control on the blow-up set for the curvature? Is it?
Yeah, so what's going on is the curvature, so everything is smooth, so there is, so you could talk about a blow-up set sort of at infinity on the boundary, possibly, but on the interior everything is going to be smooth. So unbounded curvature in this situation is always meaning that the curvature is sort of becoming unbounded at a certain rate as you go to spatial infinity. So, yeah.
But if you start with a very weird metric, that could be dense.
No, so, but what is dense? So the point is you'll never have a singularity at any one point on the interior. So the singularities are somehow happening at infinity. So you could possibly measure that somehow, but we don't do that.
So in this flow on the disk, you start with curvature 0, And at every positive time, the curvature is also bounded? Is that what I understand is asymptotically?
Right, so the question was, you start off with zero curvature, of course, and then the question is whether for later times the curvature is bounded. So the curvature becomes infinitely minus infinity, in the sense that if you look here, the asymptotic curvature is minus 1 2t. But that's actually a lower bound. So the existence theorem is saying that the curvature is always bounded from below, always by minus 1 on 2t. And in this situation, the curvature is actually non-positive. So your curvature is bounded between minus 1 on 2t and 0 in this example.
And what's the idea for uniqueness? The idea of the uniqueness?
Ah, right. So you have to... right, so that's going to take a fair amount of time to explain, but somehow what you want to do is you can basically ultimately reduce the problem to the problem when you flow an arbitrary metric on the disk. So not the flat metric, but an arbitrary metric on the disk. And what you have to really understand is if you took a smaller disk, so if you take our flow, okay, for a start, I should say what this maximally stretched concept is to answer that. So maximally stretched means it always lies above. It's what the logarithmic fast diffusion people would call a maximal solution, although that means more than one thing here. So our solution will always lie above any other solution, whether it's complete or not. So somehow you just have to make sure that our solution can't lift off some other instantaneously complete solution. So what we have to do is we restrict a smaller disk, and then we imagine a competing flow. No, we sort of imagine a flow which is a little bit bigger than ours by restricting our flow, our initial metric, to the smaller disk, and then setting the boundary conditions to infinity. So then we prove what end up being quite delicate estimates to compare that with an arbitrary solution. So it's not a really good answer, but maybe a quick answer would be you use very delicate integral estimates with the right cutoff functions.
Right. Yeah, another question here.
So if you have a flow that hits unbounded curvature in a finite time, can you approximate that using flows that are always bounded?
Right. So the question is, if you have a flow where the curvature is initially finite and it becomes unbounded, can you approximate it by flows where the curvature is always bounded? That's actually a very good question. I'm not sure the answer to that. Yeah, I'm not sure. I'll have to think about that.
Are there further questions or comments? So, if not, I'm going to convey on behalf